Inferential statistics allows us to ask questions about population parameters without having to gather data on the entire population. So this is almost like a shortcut. Maybe I want to ask a question about the population. What is the average number of something for a certain population? Rather than asking or surveying the entire population, I can create a confidence interval and have a certain level of confidence that that interval will contain the population mean that I'm looking for. Let's talk about how to do this. First, we're using the central limit theorem to create a distribution of sample means. This distribution will become taller and more narrow as we increase the size of our samples. And as that distribution gets taller and more narrow, it starts to target the population parameter, the population mean. So if we were to allow our sample size to get really, really big, then this normal distribution would kind of look like a tall, skinny line right on top of the population mean. But remember, we're trying to avoid gathering data from the entire population. So having a very large sample kind of defeats the purpose. Instead, let's gather a sample and calculate the mean for that sample. This is going to be a point estimate. And this point estimate could be used as an estimate for the population mean. However, it's not very likely that it's exactly equal to the population mean. And so suggesting an estimate that's very precise, most people won't buy it. Instead, we're going to allow for some error and create an interval, a range of values that we're saying in this interval, the population mean exists. This is what we call a confidence interval. We take a set of data, gather a sample, build an interval around a point estimate, and we say within that interval is the population parameter that we're looking for. Confidence intervals are built based on confidence levels. A confidence level is going to tell you the success rate of this procedure of building confidence intervals. For example, if we have a 90% confidence level and we build 90% confidence intervals, we can say that 90% of the intervals that we are building will contain the true population parameter. To build that interval, we gathered a sample, calculated a point estimate, and then allowed for some error to create a range of values. Let's say that we repeat this process. So I take another sample, calculate a new point estimate for that sample, and then allow for some error. I've made two intervals. They've both overlapped with the center of our distribution, suggesting that they do contain the true population parameter. If we continue doing this with a 90% confidence level, 90% of these intervals will accurately contain the true population parameter. Notice out of the 10 intervals shown on the screen, only one of them does not overlap with the blue line in the center of our distribution. That implies that that interval does not contain the true population parameter. So the fourth interval down from the top does not overlap with the blue line. That represents the 10% of the time that these intervals that we're building will not contain the true population parameter. To calculate this error that we allow in the confidence intervals, we have to talk about critical values. For a 90% confidence interval, we basically consider the center 90% of the data from a standard normal distribution. We know how to find the z-scores that carve out the center 90% of data, and we're able to find that that's negative 1.645 on the left, positive 1.645 on the right. These values separate the inner 90% from the outer part of the data. To find that outer part, we just subtract the 90% in the center from the total area, and we find that there's 10% outside of the z-scores that we've found. So 100% minus your confidence level gives you what we call an alpha, and that alpha makes up the area in the two tails. In this case, we can just split alpha into two to see that each tail contains 5% of the area. So a 90% confidence level is associated with a 10% alpha, or rather a 5% area in one tail. The critical value that's associated with a 90% confidence level is the positive z-score that we see on the screen. Notice the two z-scores in pink, they're the same values but opposite signs. So the critical value that we use is the positive z-score. We have a critical value of 1.645, and the notation that we use here is z for a z-score with a subscript that's equal to alpha over 2. So for a 90% confidence level, we have a critical value of z sub 0.05, which is equal to 1.645. Now we can talk about the error that we need to build these confidence intervals. The error-bound mean is a product of the critical value, z sub alpha over 2, and the standard deviation from our distribution of sample means, sigma sub capital X bar. We know that for a 90% confidence level, that our critical value is positive 1.645, and we know how to find the standard deviation for the distribution of sample means, assuming we know the population standard deviation. Now, admittedly, that's not very common, but this is like a training wheel problem. We're going to try it this way first, and then we're going to learn how to do the problem in a more realistic setting. So we know that for a standard normal distribution, a z-score tells you how far away from the center you are. So a critical value of 1.645 is telling us how far away from the center of the distribution we are. We use that distance to calculate our error-bound mean by multiplying that critical value times the standard deviation that we have from our sample means distribution. That allows us to see how far we travel along the horizontal axis on our sample means distribution. So every time we take a sample, calculate a point estimate, we know how far above and below we should go to make our confidence interval with a confidence level of 90%. And we know that sometimes these confidence intervals will include the true population mean, and sometimes we'll take a sample and generate a point estimate that then generates an interval that does not contain the true population parameter. So again, when we generate these intervals, we don't guarantee that they will contain the true population parameter, but our confidence level tells us the success rate of the building of these intervals used to predict the population parameter. So 90% of the time we will contain the true population parameter, and then the other 10% of the time we will not. Now throughout this entire video I've used 90% as the confidence level, but that's actually a little bit arbitrary. As a statistician, you get to decide how confident you want to be when building your confidence interval. Most of the time we tend to be 90% confident or above, but it's not impossible to use a confidence level lower than 90%. You get to decide. Let's practice what we just learned. Let's assume that we are talking about statistics exam scores and that they're normally distributed. We don't know the population mean, that's what we want to build a confidence interval for, but we're going to assume that we know the population standard deviation. We're going to assume that we know it to make the problem slightly easier for now, but in reality this is not typical. We'll have to talk about how to do this problem when we don't know the population standard deviation in the next video. If we take random samples of 36 exam scores and calculate a point estimate, a sample mean of 68, we have everything we need to be able to build a confidence interval. So first, let's just pick out the information that's given that we need. We know that we're taking samples of 36 test scores and that we calculated a point estimate, the sample mean of 68. We also know that we're going to estimate a population mean. That's the thing we're building the confidence interval for. And we're told that the population standard deviation is 3 points. We want to estimate the population parameter mu subcapital X, and to do that we're going to build a 90% confidence interval. We're using a 90% confidence level, which means we're using a critical value of 1.645, and we're also going to use the distribution of sample means, specifically the standard deviation from that distribution, to calculate the error-bound mean, which is the product of our critical value and the standard deviation from our sample means distribution. That product gives us an error of 0.8225. We will use that error with our point estimate to build a confidence interval. So we'll do our point estimate minus the error, that's our lower bound for the interval, and then the point estimate plus the error for the upper bound of the interval. Now, typical rounding rules say that if you're given the statistics like the sample mean, then you're going to keep your interval as precise as the sample mean precision. So in this case, our sample mean is whole numbers, but we're talking about a confidence interval that's precise to the 4th decimal place. We're going to round this to the nearest whole number, both the lower bound and the upper bound. This would say that our confidence interval ranges from 67 to 69. And we interpret this as 90% of the confidence intervals built in this same way will contain the true population mean. 10% of the intervals that we build this way will not contain the true population mean.